Okay, this is my fourth video in the video series about how to use my software PETTaLS to simulate the response of distributed mode loudspeakers or flat panel loudspeakers in response to material design parameters, exciters, exciter placement and things like that, and then mounting styles. So I've changed this up quite a bit since my last videos, and I've added new features and I've removed a couple things. I still have more that I want to add to this, but that'll take time. So I'll talk about that in these videos. This one's going to be a short one where I just talk about different materials and material parameters. So I didn't used to have material parameter, or bulk material parameters in there, and now we have bulk material parameters. So aluminum has these parameters: density 2,700 kilograms per cubic meter. Young's modulus, this is not actually gigapascals, it's just pascals, so I need to change that at some point. 6.9 times 10 to the 10th pascals. Poisson ratio of 0.33 and quality factor of 40. Now, I'm going to address quality factor later. The higher the quality factor is, the longer the material rings for. So this is related to internal damping. A quality factor of infinity means that the material never loses energy. I don't know what a quality factor of 0 would be. That would be nothing. There is no motion in the material or something like that. But the closer or the higher this number gets, the more the material rings. And that causes sharper peaks in the frequency response. So I just estimated that aluminum has a Q of 40. That's not a total shot in the dark. It's based on measurements that I've done in the lab for years. But it is, at this point, just an estimate. So I'll need to probably follow up with more in-depth measurements as time goes by. And then I have some sandwich board parameters, which I'll talk about later. This needs to be updated a little bit as well. But so, first off, let's just take a look at how aluminum reacts with clamped boundary conditions. No box, so this is another feature that I added. If I make this box depth essentially infinite, then there's no enclosure. No stands, 30 centimeters by 30 centimeters, 3 millimeter thickness. That's pretty thick aluminum, but that'll simulate fairly quickly, so that's nice. 1 watt of input power and a free exciter magnet, so there's no spine on the back of the exciter. So let's run through that and see what that looks like. Okay, so here in the upper left graph we have our frequency response in response to 1 watt input with this 5 watt exciter. So obviously you can probably maybe be safe putting up to 5 watts in there, and that would be the maximum volume that you would get. Yeah, so sharp peaks at certain frequencies, big dips in between. So let's see. And then we have the exciter location here relative to the plate, and then I can type in any frequency I want and see what the shape looks like. Now, the way that I've reformulated this is that where there's very little motion, we don't see a lot of color. And then the too high of motion overloads the colors right now, so this is going to be scary looking. Yep, that's scary. Okay, so let's see what's happening here. 603. Ooh, spooky. Looks like Mothman. Let's go up to a higher frequency. Here's a peak at 2528. Oh, cool. That's a funny combination of modes right there. Yeah, so then the coincidence frequency is this red line. That doesn't have enormous effects here. But that's, again, where the wavelength on the panel is equal to the wavelength in air, and so sound starts beaming parallel to the panel away from the panel edges, and then as you go up in frequency from there, it starts to beam out from the center of the panel. So we can see that sort of here on the polar radiation map. As I go to really high frequencies now, we're not going to see very much motion on the panel at all. If we did see, especially because, you know, well, I was going to say because we're above the coincidence frequency, but that only matters for acoustic stuff, not velocity stuff. Yeah, so there's not much motion going on up here at high frequencies. Here's a waterfall plot of the impulse response. I need to re-tailor this, I think, to get more low frequency resolution in the spectrogram. So these results aren't wrong, I don't think I gave it enough resolution, so I gotta re-tailor that. You can see that resonant peak right here is ringing for quite a long time right there. And that was at what, 300 hertz. So yeah, ringing at 300 hertz. So this would not be a great sounding speaker, to be honest. Aluminum is not that light, so our sensitivity is on average probably in the mid 80s for 1 watt, although we do have these big peaks. We have really no response below 300 hertz, and then the coincidence frequency at 4 kilohertz roughly causes a decrease in amplitude after that. So overall, not a great speaker. Let's compare that to the exact same size but acrylic speaker now. So acrylic is less dense, so 1180 kilograms per cubic meter. It's, I think, less stiff too. Yeah, less stiff. Oops. Less stiff as well. Poisson ratio, that doesn't matter a whole lot, to be honest, and it doesn't change material to material very much. And then the Q of acrylic is very low. So Q of 8. That means basically that the material doesn't ring. So you can imagine if you tapped or flicked like a wine glass that was actually glass, or aluminum, say, if such a thing exists, or acrylic, like a plastic wine glass does not ring. It goes thud, you know. So that quality factor is low. I just estimated that it was 8. That's probably not crazy. But again, I'll have to back that up with measurements. And then this is not a sandwich board, so that's not checked. I'll come to that later. So let's compare that to the aluminum response. Okay, cool. Looks good. Okay, these kind of are overlapping now, but we can see that this is the acrylic response, and it is way less sharp in terms of the peaks. They're a lot more smooth. It's like this is like the Rocky Mountains, and this is the Appalachians. So yeah, let's take a look at some shapes here. This one probably overloads the colors. Yes. So what's funny is that this shape becomes misshapen because of this exciter right here. It doesn't want, like, it's moving out of phase with the exciter, so the fact that the exciter is there makes this have a weird shape. Let's look at another higher frequency shape here. So like 834, there's kind of a little peak there maybe. Yeah, sort of. Okay, so that's where the exciter is, and then the most motion is there, obviously. Now we kind of have, this was overlapping, we still have the old coincidence frequency here for the aluminum. but the new coincidence frequency for the acrylic is here, and then this blue line is the frequency where the dimensions of the exciter start to affect the radiation. So both of those things kind of overlap, and both of those will cause a decrease in amplitude overall above those frequencies. So these two things, that's maybe that you could define that as the high frequency limit of our speaker. After that, there's probably not a lot happening. We can go up to a high frequency and see, yeah, see, once we get to wavelengths that are smaller than the exciter shape, the panel just doesn't move anymore, except for where the exciter is. Yeah, we can sort of see that there's some motion going on here at slightly lower frequencies. Yeah. Okay, waterfall plot. Again, I need to increase the frequency resolution of this waterfall plot. I just need to retool the spectrogram calculations. But yeah, so the lower Q decreased the sharpness of these peaks. It should have overall decreased the decay time of the impulse response a little bit. Although what's funny is that decay time is proportional to frequency, so now that this peak is less sharp but also lower frequency, it might have still a long decay time relative to how long this one was, because this one's sharper but also higher frequency. So those two things counteract each other. Okay, so let's compare that now to a steel plate, which is a material that I would never recommend using as a speaker, unless you absolutely have to, which maybe in some industrial applications you would need to use steel. Steel is really dense, it's really stiff, Poisson ratio, whatever, it doesn't matter. And then it's metal, so I gave it the same Q factor as aluminum, and it's not a sandwich board. So same dimensions, let's compare that to these other two materials. Well, there we go. Okay, so steel, actually steel, has more or less the same response as aluminum. Maybe the resonant frequencies are shifted down slightly in frequency, but looks like it's relatively similar to aluminum in terms of where those resonant peaks are, and the coincidence frequency is basically the same. So that's kind of interesting. It's just so much more dense that the volume is lower overall by probably 10 dB or so relative to aluminum. So yeah, I wouldn't use steel. I mean, obviously aluminum for the same exact shape is going to get you more or less the same resonant frequencies, but 10 dB more volume. Yeah, so that's interesting to see. All right, so let's clear out those results, and we'll go to Gatorboard now, which is a sandwich board. Now, I programmed in some equations for the sandwich board stuff, which apparently a good way of modeling these sandwich boards is to treat the low frequencies as being dispersive, which means that the speed of wave travel in the material is proportional to frequency. It's proportional to the square root of frequency. And then above a certain cutoff frequency, which I've called FC, the speed of sound is no longer proportional to frequency, it is a constant. And so for each material we have to define what that cutoff frequency is, and it depends on the squishiness of the core of the material, more or less. I think based on my measurements for Gatorboard of this thickness, 3 millimeters, it's probably going to be something like 5 kilohertz for a cutoff frequency. This is a work in progress right now. I know that this model is one that accurately models these types of materials, but I don't know for what for each thickness what the cutoff frequency is. So it's a work in progress. This is just a guesstimate right now. But okay, so Gatorboard has a really low density. That's what makes it so loud. Lower stiffness too than all the other materials, so you can bend it a lot more easily. And quality factor I put as 20, so that's in between one of the metals and the acrylic. So let's just look at, for the same dimensions, what this speaker would sound like. And I'm going to clear away all of these results. Okay, cool. So there's our Gatorboard response. Now, something that I need to update, which I've known about, is there are some inaccuracies at high frequencies, which is up here in the polar plot. And the reason why I did that was for speed. So because the wavelengths in the non-dispersive material get a lot shorter, for the same frequency range, I have to simulate the panel to way higher spatial resolution. And so just for the sake of speed, I cut down some of that spatial resolution here, and it is causing some inaccuracies up here at the high frequencies above the coincidence frequency. So when I'm going to do a different video on just purely sandwich board stuff, and I'll have that fixed by then. It's not anything major, but it is. If you're going to look at this and say, "Oh wow, look at what that does at really high frequencies," it's not 100% accurate up there right now. It's missing some radiation here at the edges. So, okay, one thing to notice immediately is that the sensitivity of this speaker is very high because it's so light. And I know from personal experience that even just 1 watt into these sandwich board materials is pretty loud. So this might be a little inflated. Maybe it's like 105 dB sensitivity. That seems maybe a bit high to me. For 1 watt, but I don't know, at 1 meter, I don't know. Again, that's based on measurements that I took off the data sheet for how much force this is going to put out at 1 watt. So I'll have to go into my lab and confirm that at some point. Let's look at some shapes just to show that it still works. Oh God, that's scary. It overloads the colors at some points, so those colors just turn red. 1250. That's less scary. So let's see what's happening at high frequencies then. So like 9200 hertz. Yeah. Okay, so yeah, that's interesting. Yep, that's what sandwich board materials do. So the other thing that I wanted to talk about was the effect of the quality factor. Now, when I go and select a material, it'll auto-fill in all of these material parameters for me. But if you don't trust me, you can go and change these yourself. So I could make this 20,000 if I wanted to pretend that this was the most dense sandwich board material on the planet, and then run the simulation. But we can also change the quality factor. So let's just, for the fun of it, change this Q to 1 and see what that does to the output. So a quality factor of 1 would be an extremely dead material. The energy does not ring, it just dies out immediately. So, oh, and I have to change this back to 5,000 to have it match the previous simulation. Okay, let's check that out. Oh my gosh. Okay, so there we go. A Q of 1. That's a good sounding loudspeaker there, apparently. Totally flat frequency response. Not bad sensitivity, obviously, like 100 dB. Let's look at what the heck the surface is doing. It's probably not ever going to be doing very much of anything. Yeah, as you can see, the the low Q keeps the vibrations from pretty much spread. There's no modes anymore or anything. Yeah, it's just immediately. I mean, this is more or less just having a piston loudspeaker, which has an omnidirectional frequency response up to a certain beaming wavelength and flat frequency response. So, yeah, I mean, if you can find that, I guess it's not a bad response. It's gonna, you know, not sound very lively, but seems to work well. It doesn't make very efficient use of this 30 centimeter by 30 centimeter space. Like for the same thing, you could just buy a, little, like coax full range loudspeaker. Yeah, it's interesting to think about though, if you can really get the damping up super high, what this looks like. Okay, so let's compare that then to a really high Q. Let's make the Q just 100, not 1,000. I don't know, 1,000 is going to be really weird looking. So let's just make it 100 and see what that looks like. This would be a material that rings for a really, really long time when you tap it. So let's compare that to the Q of 1. Oh my gosh, okay, look at that. So yeah, that's a really high Q sandwich board. Now the Q is not just affected by the quality factor of the material. The quality factor of the exciter has a lot to do with the shape of these peaks as well. So these are somewhat limited by the exciter itself. If I put in a point force exciter that has no resonance associated with it, these are going to get sharper. But yeah, you can see that now we've got a lot more sharp peaks and things going on here. And before, we saw that energy was not spreading throughout the panel. Why isn't that working? There we go. And now, obviously, the vibrations are spreading through the panel, even up to high frequencies. Wow, that's funky. Yeah, the modes like stay very regular with a Q this high. That's funny. Yeah, it still looks like checkerboard patterns because the modes are not being damped out very much. Ooh, that's funny. A lot of like weird Mothman looking things tonight. Yeah, so that's the effect of Q. Now that I said it, I want to just compare that to the exact same thing, but using a point force exciter, where the resonant properties of the exciter don't limit the resonant properties of the modes themselves. So this is the last simulation that I'll do in this video. Yeah, there we go. So, yeah, we can see that the peaks are now a lot sharper without the effect of the exciter in there, limiting them. We probably get even some funkier shapes going on here. Maybe not. Maybe at some frequencies you do. I don't know. long decay times in the impulse response. So this is going to sound a lot like this, which doesn't sound good necessarily. Yeah, interesting response. So which one of these sounds better, low Q or high Q? Well, I don't know. I mean, depends what you're going for. If you're a recording engineer, do you want a dead room to record a band in, or a live room? I don't know. Depends what sound you're going for. I mean, it's a different sound either way. Like if you're playing guitar, do you want clean or distortion? Well, it depends what sound you're going for. Usually people have a preference. So these are going to sound different, that's for sure. Which one sounds better is totally up to you as the designer. Okay, so I'm going to sign off there. This video is probably long enough. There's a lot of other stuff to talk about in here, and I'm going to keep talking about these things as I keep updating the model. So yeah, next video will probably be either about enclosures or about sandwich board stuff. So stay tuned. Hope to see you watching the next one too.